Good afternoon. Greetings. After a successful day one, we have the second talk of our symposium by Mr. Satyam Sahu on the topic of large area mechanical exfoliation of 2D materials on metallic substrates and the underlying physics. Our Foundation Week program is sponsored by Global Scientific and with support from the School of Physics IISER-TVM. Mr. Sahu is a BSMS B'16 alumni of IISER-TVM and is currently a third year PhD student at J. Herovsky Institute of Physical Chemistry of the Czech Academy of Sciences. At IISER, he has been part of several co curricular activities and has made notable contributions as the finance head and event manager for both Science and Technology and Cultural Council between 2018 and 2021, and the governor of IICM 2019. His research at IISER included major project work with Dr. Rajiv Kini on low temperature studies of 2D materials and a minor project with Professor Mahesh Hariharan. Currently, he's working on the preparation and characterization of the large area flakes and is also interested in the low temperature physics and the optoelectronic properties of exotic 2D materials. Please stay on mute throughout the talk and save your questions for the end. Now, let's welcome him to deliver his talk.
Yeah, thank you very much. Just a second. Yeah, I'll just share my screen. So it's visible. It should. Okay. So thank you very much for inviting me to give a talk during the Foundation Week of Physical Society. Today I'll be discussing a bit about what are two-dimensional materials and what we define as the large area when we think of two-dimensional materials, and I'll be showing how metallic substrates are important when you try to exfoliate two-dimensional materials. Before that, I would like to tell you a bit about my institute and department. So we are a group of scientists who are working in the electrochemical materials department of the Jerovsky Institute of Physical Chemistry. I'm also affiliated with the Faculty of Mathematics and Physics at the Charles University. As the name of our department says, electrochemical materials. We do a lot of electrochemistry, and with that, we do a bit of spectroscopy, but most of the time we try to combine these two techniques together, that is, spectroscopy and electrochemistry, to study the material systems. I was told that there will be some first year students as well. So I thought of giving some basic introduction to what are like the two dimensions in general, and then a bit on the spectroscopic techniques as well, because you didn't have any course, and I do not want the first year guys to be left behind when I go in the details of the systems. Here is the outline of my talk. So I'll be first giving a brief introduction of the spectroscopic techniques and two-dimensional materials, and then I'll go in the details of what are two-dimensional materials, how we can synthesize them, their properties, and the most of my talk will be based on the metal-assisted exfoliation, where I will show how the different metals work and how they can change the properties of the systems. And finally, towards the end of my talk, I'll show you a bit of other things that we are doing in our group. Yeah, here we go. When we think of the solids, we usually define them like in 3D. Whatever you think of it in the world is mostly the 3D. So as you can see here, like for the 3D, you have at the lower panel, you have the density of states, which are like mostly parabolic in nature. Then if you reduce one of the dimensions to less than 100 nanometers, you make it to two dimensions. And as you can see here, the density of states have already started to become discrete. So I should tell you that density of states is related to the availability of bands in which the electrons can go. I won't be going into much details. You will be studying these things during your condensed matter course. And similarly, when you reduce two of the dimensions to less than 100 nanometers, you are in the quantum wire ranges, which is like 1D, and finally the quantum dots, where you have like very discrete density of states. Also, you can define the solids in terms of their conductivity. So you have the metals, semiconductors, insulators. So you essentially have the valence band and a conduction band. So when these two bands are overlapping, you have the metals which have like amazing conductivity in 10 raised to power 6 to, yeah, 10 raised to power 6 Simon per centimeters. But when there is some gap between these two bands, so if the band gap is less than 3.2 electron volts, we call them the semiconductors. So why we choose 3.2 should be the question here. So if you try to just convert this 3.2 to the wavelengths, you will see the number should be around 400. And that's the beginning of the visible range, and most of the light you get is from the sunlight, which emits mostly the visible lights in like in the range of 400 to 700 nanometers. So which is like equal to 3.2 electron volts to something like 1.5 electron volts. So the systems which lie in the band gap which is like less than 3.2, we define them as a semiconductors. And then finally you come to the insulators. So throughout my talk we'll be discussing about this particular category, that is the semiconductors. So now I'll give you a bit background on the spectroscopic techniques or the experimental techniques that we use to study the two-dimensional material systems. So there are a lot of techniques actually, but here I'll try to focus on the most common ones, and I'll just give the brief introduction of what these techniques are and how you can use them to characterize the material systems. So the most common techniques are the photoluminescence. Most of the time I'll be calling it as the PL spectroscopy, and then we have the Raman or vibrational spectroscopy, and then finally the atomic force microscopy. So let's start with the PL spectroscopy. So the Wikipedia definition says the photoluminescence is the light emission from any form of matter after the absorption of photons. So that's how you define the photoluminescence, that you have the photons which are exciting the carriers from the valence band of the material to the conduction band. And once the electrons are in the conduction band, they always want to go back to the ground state, that is back to the valence band. And during this process they emit some light which is like of the energy lower than the absorbed light. So here if you have like h nu 1, that is the absorbed energy, so it should always be higher than the emitted energy. And if you try with the solutions, you will see this beautiful colors from the solutions which are they are emitting. So this was the very simple picture of photoluminescence, but you can make it more complicated. And especially when you discuss of the systems, you don't always have this simple thing, but it's like the more complicated picture here that we see in the Yablonsky diagram. So if you see these blue arrows upwards, so they are for the absorption, and then you have the green ones which are for the emission. But again, I won't go in the details of these systems, but I just wanted to show you that okay, there are hundreds of processes taking place inside the material systems that we can study. So then what is the use of photoluminescence spectroscopy? So if you see the left top panel here, I see I show some spectra. So it's a photoluminescence spectrum of monolayer MOS2 or molybdenum sulfide. We will be discussing quite a lot about this material. So the peak here is somewhere around 670, which exactly matches with the optical band gap of the material. So essentially, you can use the photoluminescence spectroscopy to find the optical band gap of a material system. Also, you if you try to make the heterostructures or something, I'll show you what the heterostructures are in the next few slides. You can try to understand how the charge transfer is taking place from one material to another material. And you can also study the lifetime, like for how long the carriers are staying in the conduction band, and after that they are coming back to the valence band. So I'll be discussing the charge transfer once again, and this particular right hand side figure in like towards the end of my presentation, where I will be showing what we did with the flakes. For the time being, I'll be discussing the next technique, which is the Raman spectroscopy. So it's a technique used to uh, study the vibrations of the material systems, which are like the fingerprints of a particular material system. So essentially, if you know the Raman spectrum of a material, you can always tell what material is it. And it's an inelastic spectroscopic technique. That is, again, there will be some loss in the energy or some gain in the energy, but when the light interacts with the matter. So uh, if we try to understand it in a simple way, what happens is you shine a light on the material, and then the atoms will start to vibrate in different directions. And in this process, there can be three like there can be three different processes. So one is that the energy is conserved. That is, whatever you are shining, the same energy will come back. And the other processes, what happens is you can either lose the energy or you can gain the energy. So these two processes are of the most interest for us. So if we see the panel C, first one is when the energy is conserved. So you have the electrons going to some virtual state here when you shine the light. Then it can come back to uh, the same level where from where it was excited. So there is no loss of energy. So it's called Rayleigh scattered light. Whereas in the other two processes, what is happening is like you're exciting the electrons, but they are coming to some different state, losing some energy. So when you lose some energy, it's called the Stokes shift or Stokes scattered light. And similarly, if you see the panel E here, you are gaining some energy. So in nature, usually you lost the energy, and that's why you see mostly the Stokes lines. And the ratio of the anti-Stokes to Stokes is governed by the Boltzmann distribution, and it says that in 99.9% cases, you will be seeing the Stokes, and only in a less than 0.1% case, you will be seeing anti-Stokes. So uh, I'm not saying that anti-Stokes is not important. Like, it's also important in some materials. Anti-Stokes are even like more intense than the Stokes lines because of the different processes taking place inside the material system. But don't worry, we won't go in the much details of that system as well. So for us, the most interesting thing is the Stokes line here, and obviously it was discovered back in 1928 by Professor C.V. Raman, and he won the Nobel Prize for that in 1931. Then here I show you the example spectrum of WSE2. So here we see the different modes, like different peaks, I would say. So here this is a major peak, and then you have two other peaks. So the nomenclature is again governed by the group theory. So we won't go back in the details. But if we just try to see how the atoms vibrate here, so here you have the selenium atoms, which are orange in color, and then the tungsten atoms W, which are bluish in color. So for the E2G modes, they are vibrating in like two different directions. So the selenium atoms are going to one side, but uh, tungsten on the other side, which is like defined as the E2G mode. Then you have A1G mode, where the two selenium atoms are going in the opposite directions. And similarly, you can define the B2G mode. Then next, we just go to AFM quickly. So it's a technique that can tell us how thick the material is, and how its topography is, if there are some defects on the surface, or if some grain boundary is something that you can study using the atomic force microscopy. So that's the technique we actually use to estimate the thickness of our material system. So the concept here is very simple. You have a sample here, and then you have a tip here. So tip moves like the sample moves on the piezo surface, and mm, tip probes the thing, and then you can see the signal through some electronics, like in the most simple way. And from there, the signal can be converted to the height signal or topographic signal accordingly. So here again show you the example AFM image of molybdenum sulfide. So here If you see is the nice topography image of monolayer MS2, which was grown using CVD technique that I'll be discussing soon. And the thickness for yeah, the MS2 was roughly 0.8 nanometers. So this thickness says that we are in the two-dimensional regime because it's again less than 100 nanometers. So that's all I wanted to tell you about the spectroscopic techniques, because I do not want first years to just uh, running behind the thing, and they don't understand anything what's happening. So now I'll be going to what are the two-dimensional materials, like which is the most interesting part of this talk. So so it was when we talk of the two-dimensional material, the first material comes to our mind is graphene. So it's just the one layer of graphite that you use in pencils. So it was the first two-dimensional material which was discovered back in 2004, and actually it was a Nobel Prize-winning discovery because for the discovery of graphene, Professor Sir A.K. Geim and from Professor K. Novoselov from the University of Manchester won the Nobel Prize back in 2010. So actually, what happens is graphite, like in graphite or any other two-dimensional materials, the layers interact with each other through the weak van der Waals force, and the atoms interact with each other through the covalent bonds, which are like much stronger than the interaction between the layers. So in that way, what happens is you can uh, take out one layer and you can reach to the two-dimensional regime. So graphene has like very nice properties, but since I'm more interested in the MOS2 and other semiconducting systems, I'll be discussing more about those ones. So graphene is not alone. There are a lot of material systems. Like in past 2 decades, almost 2000 new two-dimensional materials have been discovered. That is almost 100 materials per year. So if you start to write papers, you can have like 10-20 nature papers per year essentially with just by the characterization of these material systems. So you have materials like graphene which have just the same kind of atoms. So for example, you have graphene and phosphine, silicene. So phosphine is just a layer of phosphorus atoms, then silicene the silicon atoms, and likewise then you have something like the black phosphorus like material. So there you have two different type of atoms. So again you have something like boronitride as an example, and then the major part of this family covers the TMDs, which are called transition metal dichalcogenides or transition metal uh, dihalogenides. So we'll be discussing more about this family. So essentially, in this type of material, what happens is you have a metallic atom from the transition metal family, and then you take a non-metal. So, for example, mostly the chalcogens and halogens. So you can have like molybdenum sulfide, which has molybdenum as the atom from the transition metal family, and then sulfur from the chalcogen family. And likewise you have ruthenium chloride, where you have Ru from metallic family and chlorine from halogens. And likewise we have different categories, the magazines, COFs. I don't know what they are, we don't care about them. Then there is something called perovskites, and many more are coming. So the interesting thing about these materials are is like they are actually very thin, obviously. Then since they are thin, they are lightweight. Most of them are conducting in nature. For example, graphene. So it's a very good electrical conductor. Like it's much better than copper actually. Then some of them are transparent in nature. Then they are strong. Again, the graphene is very strong. It's hard, and some of the TMDs are bendable in nature. So actually, that's why you can play around with these materials, and you can have like a lot of different kinds of studies. You can also make the heterostructures out of them. So heterostructures are nothing but just the stacking the multiple layers of different materials on top of each other. It's just like the Lego thing, where you have different sets and you just put them together to make something out of it. So these days I'm working quite a lot with these kind of heterostructures, and trying to prepare the heterostructures between the some very non-material and the new materials to see how the properties of these material systems are changing. Now, since we know that we can exfoliate these materials to monolayers, the interesting thing is when you go to monolayers, like from bulk to monolayers, you are essentially going from 3 dimensions to 2 dimensions, and while changing the thickness, you are changing quite a lot in their properties. So, for example, if you see the top panels here, so when you take the bulk MOS2 again, here you have the maximum of the valence band. I hope you are able to see my cursor at least. So yeah, so we have the top of the valence band here, and then the bottom of the conduction band. And if you see, like they are at two different points in the, let's say, along the in the x axis. So here one point is at something called gamma, and then other is somewhere between k and gamma. So when you have this kind of systems, these are called indirect band gap semiconductors. So when you have materials in bulk, they are mostly the indirect bandgap semiconductors. But when you exfoliate them to monolayers, let's say, what happens is the maximum of the both, like maximum of the valence band and the minimum of the conduction bands shift to the same position, which is at k point, and then it becomes the direct bandgap semiconductor. So in such cases, the carriers can easily go to the conduction band when you excite them with the light, and then they can again come back to the valence band emitting some light. So here if we see the left bottom panel, we have the thickness dependent photoluminescence spectrum, again of molybdenum sulfide. So if you we see here, like the red color one, which is like for the monolayer MOS2, we have very high emission. But as you start to increase the thickness, the emission is decreasing crazily, and like for something like 5 to 10 layers, there is almost nothing at all. In the right bottom panel, we see the Raman spectrum of MOS2 for different thicknesses, and we see that okay, also the peak positions are changing with the increase in thickness. For example, here, which is around 385, is moving a bit, and again another one is around 405 is also moving, which shows that okay, we are also changing the vibrational properties. So this was more about the optical properties, that you change the emission, you change the vibration properties. Not only that, you also change the electronic and magnetic properties. So here if we see with the thickness, the its mu is the mobility or the conductivity of the system. So if you see that as you change the thickness here, you are increasing the mobility. Similarly, the work function can also be tuned by just by tuning the number of layers of the material system. So work function is just the amount of energy needed to bring the like yeah, take out the electron from the valence band. Yeah. Then not only that, you can also change the magnetic properties of the material system. So if you see here for monolayers, there is almost nothing. But when you increase to like 16 layers, you see the nice hysteresis loop. So shows that we have the diverse range of properties that can be tuned when you go from three-dimensional systems to the two-dimensional systems, and as a result of which you have hundreds of applications of these material systems. So you can use them for sensors, memory, CPU, and there are many other applications coming soon, like for the data storage and other stuff. So that's why it's quite important to study these materials and try to tune their properties so that you can extract something like very important out of it. But now the question is, for any of these applications, you need to prepare these materials. So how do you do that? So which brings me to the most important part of this talk, which is the synthesis of the material systems. So we have the different techniques here which can be used to synthesize the monolayers of this material system. So some of these techniques are called the bottom up technique, where you start from the atoms and then you make the monolayers, whereas some techniques are called the top down techniques, so where you already have the crystal and then you try to peel it off. So for example, the top two techniques, that is mechanical cleavage and liquid vapor exfoliation. So these are the two examples of top down techniques. So here you take the crystals and then you try to peel it off so that you can achieve the monolayer regime. Whereas the other three techniques, that is the chemical synthesis, CVD, chemical vapor deposition, and physical vapor depositions, are mostly the bottom up techniques, where you start with the atoms and then you create the monolayers of material systems. So then, if we discuss the mechanical exfoliation, what happens is, like, it's the most fundamental techniques, and the guys who won the Nobel Prize used this technique. They started to work with the tape, and they were always playing, and someday they saw something interesting. So essentially, what happens is, you have a tape here, like the green color one, and then you put the bulk crystal on top of it. Then essentially you fold the tape a few times so that you can have the uh, division of the crystal in multiple parts, and finally you press it on the bottom substrate. Or the substrate is something which you use as a base for putting the materials, and finally when you remove, you have the nice monolayer flakes. So uh, so here, so the advantage of this kind of technique is like, obviously it's easy, and like you don't have to spend quite a lot of money in making the machinery for this. You just need a tape and some crystal, and then you can play around with it. Another important thing about this technique is like the flakes you got from mechanical exfoliation are considered as the best, because they don't have any defects or other things. But on the other hand, the problems with these kind of flakes is they are like a few microns in size. So here if you see, the flakes are something like 40-50 micron in one direction, but on the other dimension is something like 15ish micron. Similarly for the other flakes here, they are like less than 30 microns, for all four. So that's the bad thing about it. Like for the industrial application, you cannot really work with these kind of flakes. For research purpose, it's amazing, but for industry it's not. And the other important factor is the luck factor for this. Like, you try 100 times and then maybe one or two times you will get nicer flakes. So that's why, like, mechanical exfoliation is good and bad in different terms. And then similarly for the chemical vapor deposition, or CVD. So is the schematic of how the CVD works. So essentially, you just put your material with substrate, and then you supply some gases. The material will go here. Like, for in general, the temperatures you needed to prepare such kind of samples, like the CVD grown samples, is around like 1000 degrees centigrades. Like, and you need a rigorous machinery to have this kind of systems, and that's why this one is like much more complicated. So uh, but the advantage of this system is like, you can have very big size flakes. You can have centimeters big flakes at least. But on the other hand, as I said, it has many crucial parameters. So you need very high temperatures, you need the machinery and other stuff. And over that, the problems with this, uh, the samples prepared using these techniques are like, they have different kinds of defects. So here if you see, it's the AFM image, or atomic force microscopy images of the samples prepared using chemical vapor deposition. And if we see just the panel, we see a lot of boundary like structures, so which are essentially the defects here. So when you have the defects in the systems, they can completely change the properties. So it's not ideal to use such a defective samples for the applications. So essentially, this brings me to the end of the second part of my talk, where I wanted to discuss a bit about the two-dimensional materials. Now, it's a major part which I'll be discussing is the metal-assisted exfoliation. So here, it's a new technique, and like people have started working on this technique like almost 7 8 years back, in 2014-15, where like some people were doing something else, and they they got some unexpected results. So we call it metal assisted exfoliation, because here what we do is, first, on the base substrate we deposit some metal, and then we put the tape with the crystals, and finally you have the very large size flakes. So here, if you see the bottom panel, actually you have the monolayer flake of roughly like 7.5 by 5 millimeters, which is like much bigger than what we observed here for the mechanical exfoliation, which was like in several microns. So uh, that's why like this technique is important, and like my supervisor was one of the first ones to identify this technique. So now the question is, uh, okay, so maybe I'll show you some more images of the crystals exfoliated using this method. So we have like the black phosphorus and the ruthenium chloride and some other crystals, and then you have like some exotic materials like the palladium tellurides, platinum selenides, and then we have some more crystals here. Like this was a crazy guy Huang, who tried to like exfoliate, I think, some 40 50 crystals, and they published very good paper after just by exfoliating the crystals. So the important thing is, what are the important factors that you should keep in mind when you try to exfoliate these material systems, especially on metals. So first thing is the uh, time for which the metal layer is under the ambient conditions. So what actually happens is, when you deposit the metal on top of the substrate, it will start to like get oxidized, and then some hydrocarbons will sit on it, and some other contaminants. So once uh, you deposit the metal, you should immediately try to exfoliate the flakes on top of it. And if you don't do it, because of the contaminants, you won't get very nice flakes here. So if you see the panels from A to F, what happens is, here we deposited gold in this case, and then we exfoliated materials on top of it after different time periods. So like in the panel A, when it was exfoliated immediately, like after 0 minutes, and we have the very large size flake. But as you go to the 6 minutes, you already start to see some cracks here. After 9 minutes, you see the bulk has already started to come, and the yield of monolayer has also started to go down. Similarly, for like 10 minutes, most of the bulk is there. 12 minutes, almost bulk is there, and like 15 minutes, there is nothing. So this can also be seen here in panel G. So as you are increasing the exposure time along the x-axis, you are reducing the yield of monolayers, which is like the red histograms here. So for 0 minutes, you have almost 80% yield. For 4 3 4 minutes also, but as you go down to 5 6 minutes, you see the yield of monolayers has decreased crazily. The similar thing is also plotted here, and here we show the schematic how the contaminations affect the yield. Now the another factor that affect the yield is the roughness of the metal. So like when you try to deposit metal, depending on what machinery you are using, what technique you are using, the roughness of the metal could be different, and as a result of which the yields for the different deposition techniques would be different. So here we deposited two different thicknesses of gold actually. So for 7.5 nanometer gold and the 100 nanometer gold, and what we observed was the yield of monolayers was roughly 100% when it was 7.5 nanometer gold. But when it was like 100 nanometer gold, it was mostly like 10% ish. And then we tried to understand why it happened. Then so we did some atomic force microscopy again, and we observed that the roughness for 7.5 nanometer gold was roughly 0.68 nanometers, whereas for 100 nanometers it was 1.43. So like it was much rougher in comparison to 7.5 nanometers. So like these are the two major factors that we should always keep in mind when we try to exfoliate materials on metallic systems. So one is that we should avoid the contamination. Second one is the roughness of the metal surface. So that's interesting, but at least we are able to exfoliate large size monolayers on the metals, like especially on gold. But does the does the method really works for other metals as well? So that's the question we had when we started to work on this thing, and then we tried to exploit different metals here. So if you see the panel B, for gold we have like the very large size monolayer as can be seen, but then for palladium, the size was smaller. For platinum as well, so silver as well. So there's definitely a question why gold works better than any other metal. So here also we can see the yield. Again, for gold, we have the like almost 10 millimeters size, which is like 1 centimeters size monolayers. But for the other materials, it has decreased. So definitely the gold has something which allows the exfoliation of large area monolayers. So there's the question we want to answer, and like there are different theories actually. So I won't be going much in the details of the mechanism why it works, but I'll try to explain it in a simple way. So what happens is, like whatever metals we have seen here are all the noble metals. So what happens is, like when you have the noble metals, they do not react with the atmosphere immediately, and the nobility of these metals is defined as by the standard redox potential. So if the metal has the high standard redox potential or the redox potential, that means it is like it does not react much with the environment, or like it does not react at all. So as you reduce the standard redox potential, as you can see here, the o- like the material starts to react with the atmospheric contaminants, and as a result of which you see that the yield is decreasing. So for example, for gold we have the redox potential of something like 1.5, and that's why we have this amazing yield. But for platinum, palladium is nicely reducing. Then the question comes is why the yield was a bit higher for silver in comparison to platinum and palladium, even though the redox potential was lesser. So that was actually explained using the strain. So let's come to this table. We see that the strain for platinum and palladium is much higher, and that's why they does not work nicely, for example. But for silver, like the strain was lesser. Sorry, it's other way around. So for platinum and palladium, the strain was lower, but for silver, the strain was higher. Also, the binding energies, which are also an important parameters, because the binding energy suggests the interaction between the metals and the material system. So if we you have the smaller values of binding energies, understands like there is some particular combinations of these two parameters which decides the definition why gold works better and not the other metals. So we don't try to go in the much details of it, and like there are some different theories which also suggest that okay, there is some quasi covalent type bondings which actually explains nicely how the wave function of material is changing when it's interacting with the metals, and how it's allowing. So again, that's the more of the theoretical concept. So let's see the factors uh, or the properties of these systems, and let's try to compare them with the substrates which are non-metallic in nature, or the dielectric substrates. So here we try to compare actually the Raman of like the Raman or vibrational modes of molybdenum sulfate when it is on the dielectric substrate. So it's a black one, and on gold, which is like metallic substrate. So if we see that we have the E mode here, which moves a bit to the left when it's on gold, and similarly when another mode which is around like 405 has also moved, and actually it has also splitted to two different modes, which suggests that the metallic substrates are heavily affecting the properties of the material system. So as we can see, like the E prime modes is essentially meant for the strain in the material system or the MS2 system. So what happens is, if there is some change in the E mode or this particular mode, we can always tell that this is coming because of the strain. Similarly, the other mode is for the charge doping. So when you have a material on top of metals, it's possible that the electrons are going from one metal, like from MS2 or the TMD to metallic surfaces, and as a result of which there is a shift in it. So then we try to compare it for different metals actually, and as can be seen, like the dashed line is this for the silicon, and then like silicon oxide, and then for different metals we try to see how the strain peaks are changing, and we observed that for palladium it was like 0.7% of strain, whereas for gold the strain values increased to up to 1.5%. And again, here we try to compare the sizes and the strain for the different metals, and we see that the yields are again very low for these palladium and platinum, but for silver and gold, and they are still bit better. Then we try to calculate the density of states, or the available states that electron can occupy. So again, if you see the bottom one is a freestanding when you don't have any substrate. So we can nicely see the gap here, like from zero point 0.0 to something like 1.2, there are no states, which essentially means that you have the band gap of roughly 1.3, 1.4 electron volts here. But when you have the TMD material or metallic substrates or gold, you see there is no space at all, which suggests that when you have the TMD materials on metallic substrates, you essentially close the band gap between the two bands, that is the valence band and conduction band. And actually, as a result of which, we don't see the photoluminescence as well. So again, we are here comparing the photoluminescence for MOS2 on different substrates. So the uh, bluish one here is for MOS2 on the dielectric substrate, and here if you see the orangish, which is for like molybdenum sulfide on metallic substrate, so you clearly see that there is no emission for MOS2 which was on metallic substrates. So actually this was nicely explained by the theory of charge transfer. So what happens is, in MOS2 you have some, like, you excite the carriers from uh, valence band to conduction band here, and what happens is, because of the difference in the work function of the two systems, the charges go from MS2 side to the metallic side or to gold, and as a result of which you don't have any electrons here to recombine with the holes and to emit light essentially. So that's why we do not see any emission here from MS2 on gold. So that's that's amazing. Like you can exfoliate large size flakes, but they are useless, because you are changing quite a lot of their properties. You are changing the band gap, you are changing the emission and the strains and doping, and a lot of things. Moreover, say if you have the metallic substrate at the bottom, you cannot use those systems for any of the electronic studies, because for that you want the current to pass only from the material and not from the metallic substrate, because if current is passing from the metallic substrate, you don't see the effect on the material system. So for that you need a technique actually, using which you can transfer the large size flakes. uh, so for example, large size flakes to a dielectric substrate, and for which we tried to show another technique where we use a bit of chemistry. So I'll be showing this part. So here what we did was, in the first stage we tried to exfoliate the materials on gold as usual. So we deposited gold on top of the substrate, and then we put the crystal, and then we see like most of the crystal has been transferred here. So this was the technique we have already discussed. Then what we did was we put a polymer stamp on top of it, like the top on the top of the flakes which were on gold, and then we put the whole stack in a solution here, and what the solution does is it removes the gold from the surface of the substrate. So essentially, whatever flakes you had on gold will come to the polymer substrate, and the bottom substrate, which was like the this silicon substrate, will sit back at the bottom of the solution, and then you have the polymer floating on top of the solution with the flakes. So then you can actually take out those flakes with the help of a glass slide or something, and then you can actually transfer them to another dielectric substrate, so like using the simple micromechanical stage, or even just by putting the whole stack on top of the dielectric substrate, and finally you have most of the flakes transferred on the dielectric substrate. So if you have the large size flakes on the dielectric substrate, you can again study them and try to see if they can be used for the applications, like especially for the optoelectronics or sensor based applications. So that's what we did, and then here we have the pictures of the same sample before, like when it was on gold, which is like on the left side. So we had something like 5 millimeters by 5 millimeters monolayers, and then on the right side we have the uh, transferred flakes. So as can be seen, like in the inside the blue circle, we have the very nice monolayers, and then we like try to compare the two substrates, and we tried to see how much of the flakes we were able to transfer from metallic substrate to the dielectric substrate, and the yield was roughly 95%. Then we also tried to see if there are any changes in the properties. So on the left side I show the XPS, which is like X-ray photoelectron spectroscopy spectrum. So in this technique what happens is you try to see the amount of the molybdenum atoms or sulfur atoms, or like uh, what kind of atoms you have if in your material system. Sometimes what happens is like when you are using this gold etching technique, you're putting the samples in the solution. um, it's possible that some of the gold will come to your material. So it's important to see if you have those contaminants there in the final sample. So that's what we tried to study, and then we also tried to compare it with the bulk crystal of MS2, and what we observed was like there was no change. But when you have the same thing on metallic substrate, the two peaks will like not overlap for the two different systems, but they will be slightly shifted, which suggests that there will be some charge transfer. Also, we did some Raman spectroscopic measurements and photoluminescence measurements. So here again we compare like three different samples. So one, the directly exfoliated sample. So as I was showing earlier, the tape based method where we had like very small size flakes, and which were like of the excellent quality. And then we have the flakes on gold, and then for the transferred flakes, which we call as the R method. So essentially, if we see the black and blue, they are nicely overlapping with each other, whereas the red ones are shifted, as we discussed earlier, because of the strain in the E prime mode, and the charge dropping in A1 prime mode. So it suggests that the quality of our flakes is as good as the mechanically exfoliated samples on the dielectric substrate. Like those samples were very small. Then we also did the photoluminescence measurements, and again we tried to compare the samples prepared using two different methods. And what we observed was that there was not much change in the photoluminescence, and like both these peaks are like mostly comparable. Both the spectra are mostly comparable, except at some point where it could be because of some remanent strain in the system. With That's why we have slightly narrower line width here. Then we also made a heterostructure. So we stack two different layers. So we took first MOS2, and then on top of it we dropped MOSE2. So molybdenum sulfide, and then on top of it we had the molybdenum selenide. And then we tried to see the vibrational properties of that system. And here if we see in the top panel we have the vibrations for MOSE2. So we have these two peaks, and in the bottom panel we have the vibrations for MOS2. So again these two peaks. And when we have the heterostructure, we have like all four peaks here, which are like not shifted with each other, with respect to each other. So which suggests that the interaction between these two layers is minimal. So if there is some interaction between the layers, then you will see the shift in the vibrational modes, as well as we were observing earlier for gold. Like for example here, then again we did the photoluminescence spectroscopy of these samples. So here we have the PL for MOSC2, and then for the MOS2, and then for the heterostructure. So the important thing to note here is like, if you see the PL of MOSC2 here and for MOS2 here, like clearly, and then you compare it with the heterostructure, you clearly see that here you have the high PL in the MOS2, or high emission from MOS2, but here it has reduced. Whereas for MOSC2, it was slightly lower, and then it increased. So if we try to understand what's happening here, is we can come to this simple schematic. So it's just the band alignment of the MOS2 and MOSC2 heterostructure. So here we have the valence band, conduction band for MOS2 and for MOSC2 as well. So what's happening here is most of the holes that were created here are easily moving from MOS2 to MOSC2. And similarly, the excited electrons that were in the conduction band are also moving to the MOC2 side, which says that not many electrons and holes will be there on MOS2 to recombine with each other. And that's why you see the very low photoluminescence here. On the other hand, more of the electrons and holes are coming to the MOSC2 side. So that means like uh, you have more carriers in MOSC2 side than the bare MOSC2, and that is why you see the enhancement in the photoluminescence or emission here. So then we also showed the application of the flakes prepared using this method. So what we did was we transferred the flakes on a dielectric substrate, and then on top of it we put like two electrodes as the source and drain electrodes, and then we shine the light on top of the flake, and we try to record the current, as can be seen here. So like here I have plotted the current versus voltage for different illumination powers. So essentially, you increase the laser power, and see how the current is increasing. And then like from these currents you can always calculate the response parameters of your photo detectors or sensors, and from there you can try to explain how they are comparable with the different systems. And what we observed was the parameters that we got from our samples were nicely matching with that of the samples reported earlier. So that suggests that that technique was actually uh, much nicer. So actually, this brings me towards the end of the third part of my talk. And as a summary, the take home message for us is like the gold works best for the exfoliation. As we have seen, we can have very large size flakes, but it is useless. We know already why it is useless, because you are changing the vibrational properties, optical properties, and you cannot use it for the any transport measurements. So uh, as I was discussing, we have different possible mechanisms for why the gold works better. So that's still an open question, and we are trying to answer this thing by performing experiments under different conditions to see what could be the possible explanation for why gold works better. Also, another important question is, can we tune the properties of two-dimensional materials on gold system or any other metallic system? So, for example, can we somehow change this peak positions back to the normal peak positions by the application of some external factors such as the strain or doping or something? And similarly for the photoluminescence also, uh, here if we see the like flakes are nice, but they are like not amazing. The yield is still less than 100%. So is there a better way to transfer the flakes to a dielectric substrate in a more nicer way? And something else, eh, sorry. So this brings me to the last part of my talk, where I'll just show you the other stuff that we do in our lab. So one such thing is the ultra high vacuum exfoliation that we are working on. So as of now, I was showing you the exfoliation of two-dimensional materials on either metallic substrates or dielectric substrates under the ambient conditions, in the under the ambient atmosphere. So in such cases, you could have like different contaminants, as I discussed earlier. But now we have developed a setup where we can perform the exfoliation inside the chamber, which has like almost zero contaminants at all. So like this is the actual picture of our setup that we developed recently. And here are some of the exfoliated flakes already. So this we exfoliated molybdenum sulfide on gold. So here you can see the very large size flake. And uh, on here we have the zoomed in version of the small area, and it looks like the flake is very clean. Similarly, we tried to exfoliate molybdenum sulfide on silver as well. And apparently for silver it also works amazingly. So that's one thing we have recently developed. And then this is also the important technique that we are working with in our lab. So this is called tip enhanced Raman spectroscopy. So it's just the normal Raman spectroscopy, but what we do is we use the AFM tip, or atomic force microscopy tip. And what happens with that is, like, uh, when you are bringing the tip closer to the uh, material which is on metal, uh, the incident and the emitted the electric field of the incident light and the emitted light will be enhanced by a factor of like 1,000 or something, or even more. And as a result of which, you can see some new Raman modes, or you can enhance the intensity of the Raman modes as you were seeing earlier. So like this is one of the setup that we have in our lab. And like only a few people in the world have this kind of instruments. So this is one of the reports that we recently published on the tip enhanced Raman spectroscopy. So as of now, we when we were studying molybdenum sulfide on metallic substrates, we were able to see only these two peaks. So the E peak and A1 peak here. But when we perform the tip enhanced measurements, we observed some more modes here. So like we have one mode here around 280, and then another mode around 450 ish. And likewise we did it for for different TMD. So this is for tungsten sulfide, molybdenum selenide, tungsten selenide. Then we also work a bit with the photo detectors. So this was a recent paper that we published from our group. So here we made a photo detector out of our topological insulator material, and we tried to explain the mechanism of the photo detection with the help of the photothermoelectric effect, or the Seebeck effect as we say. So in that, what happens is when you shine the laser at one particular point, you increase the temperature of that point, and the temperature at the other point is like very low, which sets up the temperature gradient, and as a result of which you have the voltage difference in there. That's what we plotted here. So here, instead of voltage, we plotted the current at different points, and we observed that how it's changing. And this shift from positive to negative in the current when going from one side to another side is the signature of the photothermoelectric effect. Then we also published this paper recently, and this is also like the photo detector, but it is based on new material, chromium sulfur bromide. Like it's a very hot material, and I'm doing a couple of projects on this material now. So here the mechanism of photo detection was entirely different from what I showed earlier. Like from here, so here we were explaining it with the help of the thermoelectric effect, but for this thing we were explaining the photo detection mechanism with the help of just the photogalvanic effect, which is like more common in the semiconductors. Then uh, we are also trying to study the wire fringence effect. So if you know, like for different materials, there is something called the anisotropy, and as a result of the anisotropy along the different directions, you can have the different refractive index. And that's what we are trying to study. Like we shine the light at different polarizations, and we at different angles, and then we try to see how the uh, intensity of flake is changing. So if you see like here at -90, there was nothing, but then at -30 or something we had something, then at zero nothing, and similarly. So which is actually the signature of wire fringence effect, or like the different refractive index along the different directions. So we are currently writing this manuscript, and then yeah, that's the most important setup that we have. So as I said, we work in the department of electrochemical materials, so we are supposed to do a bit of electrochemistry as well. So for that we developed this new setup. It's called the micro droplet setup. So in general, what happens is when you want to see the doping effects or something, in most of the labs, what we do is like um, people put a lot of electrolyte on top of the material, and like they cover the whole material in general. But in our case, we have developed this setup using which we can uh, put the electrolyte only at very small area, which is like around 10 microns. So this is an amazing setup, and like these are some of the results that we published recently. And yeah, we do quite a lot of other stuff as well. So we work with some of the batteries, like some cells, and then the low temperature studies that like we are currently working with. And then I'm also working on the anti-Stokes phenomenon in different material systems, and then spectroscopic ellipsometry, and quite a lot of things actually. So this actually brings me to the end of my talk. So with that, I would like to acknowledge my group members, our funding agencies, and for more details, you can also check out our websites. And yes, we are looking for highly motivated PhD and postdoctoral candidates. So if any of you are interested in working with us, feel free to contact my supervisor Matevelichki. you can find the you can find his email details on the websites. And we also have another position this I'm promoting for one of my colleagues from IISER Kolkata, who is now a group leader in our institute itself. So we have an open position in the electron molecule collision studies. So if you are interested or your friends are interested, feel free to contact Dr. Pamir Nag. And yeah, with that, I would like to thank you all again for listening me for 1 hour almost. And I would like to thank Physics Society of IISER-TVM. And thank you very much.
Thank you for your valuable insights. Um, we'll be taking questions now, so you can unmute yourself and ask your questions or put it in the chat.
Yeah, Satyam. Hi. Nice, nice talk. So I had a question in the 30-second slide of your
Okay.
talk. Like,
Uh,
can you go back to that slide once?
33, 30 seconds. This one.
Yeah, the one after this. Sorry. Yeah,
Okay, this one. Yeah.
yeah. So you showed that there is a shift in like the stress, like at what frequency the stress happens. Could you explain in brief, like what might be the reason for this shift?
Okay, so essentially what happens is, so as you know, like these metals are very soft in nature. So when you put the material on top of it, you try to like press them a bit, and then as a result of which there will be some surface modification of these materials. And depending on the properties of these particular materials, like the hardness and other factors, the surface will be changed accordingly. And as a result of which there will be different strain in different metals.
Yeah, but like here specifically, we see that it increases, like for in your graph, it increases. So, is there any specific property that you can point out to why such this frequency change
uh,
happen?
okay, actually what happening here is there is something called quasi covalent bonding between the TMD material and the metal. So it changes the, what do we call, the wave function of the material system and the metal as well. So if we go at quantum level, we'll have to like discuss in terms of like wave functions and all. But I don't want to go in the details, and that's why like I was trying to explain the things in easier way, that it's just the surface modification that we are doing.
Okay, okay. Thank you.
Yeah. Do we have, yeah. So yeah, if you don't have any questions, I'll just stop presenting and then probably we can discuss the stuff. Okay. So there is a question. You mentioned that gold was a good candidate for exfoliation, but not quite useful. I didn't fully understand why. Okay. So I was trying to explain that, like as I showed that gold, on gold you can have very large size monolayers. So that's amazing thing. But as we like as I showed that there will be the change in the properties, like you are shifting the vibrational modes because you are generating strain in the system. And then there is also the charge transfer, which is also affecting the modes. And another thing is that when you see the photoluminescence, there was no emission uh, when we were performing experiments on gold. I think I missed it here. So here, so like when you have the TMD on dielectric substrate, you have very nice photoluminescence. But On metallic substrate there is almost nothing. So that's why you cannot use it for any yeah, so you cannot use it for the any optical studies. Also you cannot make the devices out of it. That's why I said that it's not quite useful. And like the next question, why but isn't the large monolayer still desirable? So yes, definitely it's desirable. And now we are working on the field thing that how we can modulate these films on metallic substrates so that we can use them for the application purpose. So like if we can somehow tune the strain and the charge dropping so that we can observe some photoluminescence, and we can reduce the strain, then it's also possible that we can use go like TMDs on gold for some nicer applications. And like I hope I was able to answer your question. So I hope I was able to answer your question. Yeah, thank you. So do we have any other questions?
Hi Satyam, nice talk. So you explained the reason why this MOS2 and MOS2 photoluminescence has increased, right? By some formulable energy band diagram. So
Yes.
can you just show that once?
Sure. So this one.
Yeah. This one. Can you
Yeah.
just repeat what you said? I did not get it.
Okay. So if you see the photoluminescence spectrum of MOC2 here and then the MOS2 here, and then finally when you try to compare it with the heterostructure. So for example, the photoluminescence of MOS2 has decreased. So here like you were seeing some values, but for the heterostructure it has decreased a bit. Similarly for MOC2, here there was some value and finally like it increased by a specific amount. So I was trying to explain it with the help of a band diagram. So what happening here is, so you have a valence band here and conduction band here. So that's for MOS2 and similarly for MOC2. So because of this difference in the energy between the valence bands of MOS2 and MOC2, most of the holes can easily go from MOS2 to MOC2. And similarly, they on for the conduction band also we have some energy difference between MOS2 and MOC2. So the electrons like to go to the lower energy level before they come back to the valence band. So that's why most of the electrons are jumping from MOS2 to MOC2 side. And that's why the more of the carriers are recombining here on the MOC2 side, giving more light from MOC2 and less light from MOS2.
Okay, so your effective number of carriers is just increasing, right? That's why
Yes.
you get a high intensity.
Yes.
Okay. Yeah. Thanks. Yeah. Nice talk.
Thank you.
Any more questions? Okay. So, with that, we have reached the end of our second talk. So, I would ask everybody to stay tuned for more events we have on our way. And thank you, Mr. Satyam Sahu, for your time. And it has been a pleasure.
Thanks a lot.